So the floor is yours, Greg. You have 30 minutes, including questions, and I will interrupt you if necessary. And there's one thing I should mention. Questions should be posted in Zulip, not in the chat of the Zoom call. And the Zulip link you also received via email during the last days. So please, every conversation should be in Zulip, or ask live to Greg. Thanks.
Okay, thank you. I want to thank the organizers for the invitation and for including our paper on the program. This is joint work with Joanna Humphries at Yale and Joanna Joensen at the University of Chicago. This is also a kind of a long ongoing project. Don't want to scare the students here, but sometimes it happens. And we're in the middle of finalizing a major revision of this, and I can talk a little bit about that at the end if I have time. So in this paper, we're trying to think about complementarities in high school, in college investments. Oh, it's just slow. And there's a large literature thinking about early childhood skill formation, and a lot of that literature is trying to understand, are there complementarities between skills and investments? So if a child has higher skills, does the same reverse investment have a higher return? And this can lead to something called dynamic complementarities, where if I make an investment in a child's skills today, they will presumably have higher skills tomorrow or in the next period. And then in that next period, the returns to investments will be higher. So the return investing today will increase the returns to investments tomorrow. So we kind of want to look at this, but okay. Looking at it a little bit later in the life cycle. Okay, so we're going to be focusing on secondary and post-secondary investments. Okay, and I want you to think about three components that we're going to be looking at. Okay, and when we talk about these complementarities, so one component is going to be some a set of latent abilities, multidimensional abilities. So you can think about something like cognitive ability, interpersonal skills, conscientiousness or grit. And we're interested in how that complements or interacts with high school investments, and also how that interacts with college investments, and then also how high school investments and college investments interact. Okay, what's interesting in this setting, which is a bit different from earlier in the life cycle, is that in high school and in college, investments start to become. It's okay, and I know the microphone's working, so that's good. So I know that investments are becoming more specialized, right? So we'll be looking in the context of Sweden, and kids, when they choose to go to high school, they can go to a high school that's focused more on STEM investments, or they can look at go to a high school program that is less STEM but more on social sciences and so on. And so these investments start to become specialized, and likewise for going to college, as you all know, you tend to major in one field, specialize in one field, and now the complementarities could go in different directions, right? So if I specialize in STEM in high school, then what might happen is that the returns to doing something other than STEM could go down, right? And the way to think about this is that, in high school, I have a certain constraint of how many classes I can take, and I have to choose whether I spend more of my time in STEM, which means I'd spend less time taking other classes. The same thing goes for college. And if I don't have those investments in high school that correspond to what I see in college, then you might have both dynamic and what it looks like, what we observe is like negative or positive dynamic complementarities. So this is what the goal of the paper is. And I said we're going to look at this in Sweden. We want to be able to really dive in and look at some more detailed programs than you typically would. And so we'll have pretty small cells. So what's really great about this data set is first, we have 100,000 men. And then we have very high quality ability measures from military enlistment data which will combine with labor market education records and also health records. Okay, so this is a very rich data set that we were able to put together. And then there's two parts to the paper. And so I'm going to have to go through this relatively quickly, but we have kind of non-parametric or semi-parametric evidence on complementarities between ability in schooling. So I'll show you evidence that there's both absolute and differential sorting into high school track, college enrollment, and graduation. And there's very strong sorting, okay? And we also see strong complementarities between abilities and majors and earnings. So if I major in, for example, business, then my earnings will depend a lot more on my abilities than if I go into, for example, education. Okay, and so this is going to be important because this is, really, you say very strong sorting. You see strong complementarities between these abilities and majors and earnings. So this kind of motivates developing a Roy model of high school investment, college investment, and labor market outcomes. Okay, so we'll jointly model a sequence of educational decisions and long-run outcomes, and we'll use a model latent heterogeneity as well as choice-specific sources of exogenous information to be able to identify the model. Okay, so if you want to think about this, we have like 3 dimensions of latent ability, and then we have additional a dimension of unobserved heterogeneity that will allow us to kind of explain the correlations between these outcomes. So what do we find? More challenging high school tracks increase college enrollment and graduation, but there's strong complementarities between high school track and ability. Okay, so someone who is on average higher ability gains more from high school track. They're more likely to graduate. They'll get bigger returns to those investments. And then we see, it's not huge, but we see some evidence of this positive and negative dynamic complementarity. So if you do STEM in high school, then your returns if you go into fields that are not medicine or engineering are going to be a bit lower than if you had stayed in an academic program. Okay, and then in the paper, I'm not going to have time to talk about it today, but we're going to consider some policies, thinking about marginal incentives for STEM courses or eliminating vocational track. Okay, but I'm not going to have time to go through all that today. So again, this is a short talk. So there's a quasi-experimental literature. I'll talk a little bit more about how we see our paper relative to that literature at the end. There's a long structural dynamic discrete choice literature. I think what's novel about what we have is that we have both these multidimensional abilities and these high school and college choices that we add to the model. Okay, so just briefly about the data and the outcomes. So we have 100,000 Swedish men who are born between 74 and 76. Why between 74 and 76? It has to do with data availability and the quality of the ability measures. What's really, I think, unique or really interesting about the Swedish context is that every male in the population had to go through military enlistment. And as part of that process, they had to sit down with a psychologist and be interviewed for about 20 minutes. And that psychologist then rated them on different scales. Okay, so having that kind of high quality measure for such a large population is a really unique aspect of this data. And then for education, we're going to be looking at students starting in 9th grade, their choices in high school, enrollment, and graduation. I think we split the majors and the tracks into things that are pretty intuitive. So I'll just leave that in those categories until we talk about them later. And in the paper, we look at average wages. So it's basically the wages between their 34 and 39. But we also have outcomes looking at present value of after-tax income. Okay, so high school investment. So first, I kind of want to show you that there's important correlations here that are interesting to try to understand. So we categorize high school track into 3 categories: a vocational category, academic. So these are individuals who don't try to do a lot of math and science, and then the STEM, which is kind of technical and science and math kind of tracks in high school. And you can see that the outcomes and the choices vary quite a bit, right? So you see that the STEM track is much more likely to go to STEM in college. Maybe that's not such a surprise. The probability of enrolling in college varies quite a bit, and also the graduation rate and also the earnings, right? So what we're trying to unpack here is how much of this is going to be coming from the latent abilities that we look at, the family background, how much is coming from the actual investment high school track, or how much of it is it about them being pushed into different college decisions later on, okay? And then just to convince you that this portfolio choice problem that the students have when they go to high school is important, this is how students spend their time in Sweden in the different tracks. Okay, so the tracks we kind of aggregated like in science and technical line into like an academic STEM track. You can see that they spend about 40 to 56% of their time taking math, science, or technology classes. You can see that in terms of language and social science, languages and art, they spend a much smaller fraction of their time because they're spending so much time in these STEM fields. And vice versa, if you look at the academic non-STEM, so people who go into business, social sciences, and humanities, they spend much less time taking math and science and a lot more of their time taking social sciences and languages. Okay, so it's this kind of trade-off that the students have to choose what they want to specialize in high school that we're interested in. Okay, so yeah.
There was one question.
Yeah.
Maybe
yes.
So there was one question. So how do you deal with the initial conditions in terms of endogeneity? I mean, like many things could have been already done before high school.
So I think in terms, sorry, I don't.
So,
yeah, so we're considering basically initial conditions at ninth grade at age 14, 15. Okay. And that's how we're kind of observing that. We would like to go earlier, but we don't have any information about that. Yeah. And our understanding is the Swedish, like the schooling system is not very heterogeneous until grade 9 or until you go to secondary school. So there's not a lot of choices that the students are making. Of course, they could be doing some stuff, things outside of school. Yeah.
Hi, do you have any expression in the quality of the high school you interact? Like, for example, I'm thinking that how this can be affected with the quality.
Yeah. Okay. So the question was, and I'm going to broaden the question a bit if you don't mind. So the question is about complementarities between school quality and ability. So you might think that people of certain abilities are going to different qualities of schools, right? And that there might be an issue there. What I can say is that when we look at the returns to abilities with across schools, if we put in fixed effects for each school, it doesn't change what we find in terms of earnings and so on. So it doesn't seem that the quality is really pushing things. And you see some that also confirmed in other reduced form evidence in other countries. Yeah. Can I continue? Okay, great. Okay, yeah, I was going to talk about the latent ability factors, and I would be happy to talk about this more afterwards. So this is a kind of a big part of. We develop a measurement system, and then we estimate the measurement system, and then use that to estimate the outcome. So that we estimate this in a two-stage process using maximum likelihood. And what we get out of that at the end of the day is three abilities for each individual. Cognitive ability, interpersonal ability, and grit. We don't take names from test scores. Actually, we validate this using survey data and look to see how these factors load on different questions and surveys that are not used in the estimation, and that's how we kind of came up with these things. So the cognitive factor loaded a lot on test scores, math test scores, and kind of curiosity measures. Interpersonal skills loaded a lot on, do you spend time alone at recess? Do you like to talk in class? Do you do you like to spend time with your friends? Also, childcare was positively correlated with this interpersonal, which is interesting. And then the grit factor was loading a lot in questions like, do you do things even if they're boring and stuff like that? Okay, so yeah, or do you always do your homework and things like that? So that's kind of how we assign these three things. This is based is based on military and conscription exams and ninth grade educational outcomes. And we do account for schooling and background in the measurement system. So you can think of these as kind of residual abilities. Again, we can talk about that a little bit more later. And then one thing we get lots of questions about is, well, some of your ability measures are after the choices that are made. So for example, military enlistment is done at age 18. That's after you see some high school decisions. So we've developed an identification that is an extension of Heckman, Hansen, and Mullen that can use earlier measures to be able to get us to account for schooling after the time of the test, basically. Okay. So there's a lot going on that I don't have time to talk about in this slide, unfortunately, but I'd be happy to talk about it more afterwards. So we take the measurement system. So the measurement system gives you basically a PDF of each ability for each individual, right? And then you can take that measurement system and ask directly, what is the mean ability for each of these tracks? And you can see very strong sorting. So the way to read this is, for example, for the students who do an academic track, their cognitive ability is about 12.5% above the mean, okay? 12.5% of a standard deviation above the mean. And you can see that the sorting is quite strong in cognitive and grit abilities. So for example, the grit ability of the people who go into STEM track is about 70% of a standard deviation above the mean. So what's kind of interesting in this high school version, we see very strong absolute sorting. You might be worried about, there was a question about quality, you might also be worried about the mission system. The missions for high school is done at the municipality level, and their job is to basically meet the demand. And so in most cases, students, we have application data for a fraction of the students. We see that basically everyone gets into a track that they list as one of their first. So maybe it's not the exact program, but if they wanted to do STEM, they can do STEM, and they eventually do a STEM program. And now we can look at the sorting into college. Okay. And you can see there's actually a lot of differential sorting, right? And so students who go into business are sorting more on interpersonal and grit ability, not so much on cognitive ability. Science and math, a lot of cognitive and grit, but not so much interpersonal, and so on. And so it's kind of interesting. Some of this might be driven by the mission system. So just so you understand the mission system in Sweden, medicine and law are very competitive programs. So part of this might be driven by that. And if I have enough time to talk about the extension, I'll tell you how we plan to deal with that. But in terms of engineering programs and science and math, those are quite easy to get into because usually the supply is bigger than the demand for those kinds of programs, okay? And so again, we see some very interesting differentiated sorting. And then the last evidence I just want to show you is about complementarities between abilities and education and earnings. So we're just going to estimate a number of earnings equations for the 15 final schooling states. This is kind of hint at what we're going to be doing in the model. And so we're going to do by different major, okay? We're going to be controlling for family background, and they're going to see how these abilities, these thetas are going to be influencing earnings. And what's interesting there, okay, is that you see quite a bit of heterogeneity in the variation in earnings with skill, okay? So the one thing that I want to first point out is that business is red, and you can see across all three abilities that you see the returns are quite high for both cognitive, grit, and interpersonal ability. So if you are at the 10th decile for each one, then if you want to maximize your earnings, then you definitely want to go into business. Okay, you can see for other fields, for example, for like engineering, science and math. So engineering is a bit flatter in cognitive ability and grit, which has kind of surprised us, but actually much steeper in terms of interpersonal skills. Okay, I think the recent literature looking at engineers is in line with this because if you really want to advance in engineering, your skills become obsolete. Deming has some work on this. Your skills become obsolete at a certain time, and then becoming a manager is really the best option for you. And that's kind of what we're seeing. I think what we're seeing here. What's also interesting about this graph is you see the lines cross, right? So there isn't one major where everyone would make the most in it. Okay, and this is kind of again motivating the Roy model that we're going to estimate. Okay, so the goal is going to be to estimate a model with dynamic complementarities. And so one thing we're going to do is going to be a bit different flavor from the other papers that we've seen so far is we're not going to take a standard optimization problem of agents. If you've kind of looked at the structural literature on college major choice and stuff, it's hard to model these decisions without putting a lot of loading on preferences. So what we're going to do is we're not going to take time, we're going to approximate these decisions, okay? And so what that means is that we can only estimate ex post treatment effects. So we can say, what if we move someone from an academic to a STEM track, okay? But I can't say what happens if I change something in the information set, or what happens if I give them a grant, okay? So it's going to be a limitation. The model is a little bit more flexible, but it's going to be a limitation that there's only certain questions that we'll be able to to answer, but what we will be able to do is characterize the conditional choice probabilities and identify marginal individuals at each decision node. Okay. So let me just skip to what the model looks like. So there's going to be some courses in 9th grade that you can choose. This doesn't really push things around too much, so it's not so important. There's going to be the choice of the high school track that you do. So again, you're going to have vocational, academic, STEM. There's going to be a choice to enroll in college. There's 13 options there for the different majors or not enroll. If you don't enroll, you just enter the labor market for high school graduates. You can choose your final major. So there's going to be another multinomial choice model there. And then finally, within each major, there's going to be a graduation model. And if you don't graduate, then you fall into one of 2 labor markets for college dropouts. And we'll have 12 different labor markets for the different majors to account basically for this idea that returns to abilities are varying quite a bit between these different majors, okay? And the way we model these decisions, okay, is going to be, you could think of it as here we have probit models or multinomial logit models, okay? So we're kind of approximating the decisions that individuals are making. And the things going into the decisions, we have the measurement equations. We have very detailed information about the families and the mothers. Okay, so we have their education, income, whether they're married, what the mother's age was at childbirth. We have information about the health, which we don't actually use a lot yet, but that's something that's actually kind of interesting as well. When the men do a military enlistment, their health and strength and fitness is measured. And then we have some instruments that will vary individuals' choices going into high school and going into college. So these are within school across cohort instruments. So if in your class more students go into engineering than normal in adjacent years, then that is the variation we're using to see how people are more likely to go into it. So one way to think about that is there's these recruiters that go to high schools to get people to go to different colleges, and some recruiters might be better than others, and that could be generating the variation that we're using. No. Oh, the question was, do I have information college grades? And unfortunately, we don't. So I see it would be nice, yeah. So we see enrollment, we see if they finish the credits, but we don't actually see the grade. Yeah, I agree. That would be nice. Yeah. Okay, so I think I'm running out of time. So we're going to estimate treatment effects where we use our model to estimate counterfactual earnings, okay, depending on different choices, right? And so we've estimated these conditional choice probabilities, and then we can say what happens if we change STEM early on, and how is that going to change their enrollment decision, which major they go into, and so on. And we can simulate these things out as in any structural model. Okay, and this is what we find for returns to high school track. So what we do is we look at different populations in this graph. Okay, so we have on the left, we have the average marginal treatment effect. That's for someone who is at the margin between doing STEM or vocational. Then we have the average for the population of students. Then we have people who are above the median in all 3 abilities and below the median in all 3 abilities. And then we have treatment on the treated for those who chose that and for those who didn't choose that, okay, that made that choice. So what we see here is in general, doing more challenging tracks makes it more likely that you will graduate from college, okay? But you can see that there's actually strong complementarities, right? So you can compare the ATE for high and low ability or for TTTUT. So you see here that we have sorting on gains, both into academic and into STEM tracks. And you see that these things vary a lot by ability. There's quite a big difference. And so that's the complementarity that we see between high school track and ability going and graduating in college. And then we see something similar for wages. Okay, so we can see that individuals who go into a STEM track versus vocational, or academic versus vocational, those who have higher ability are the ones who actually get higher returns to those tracks. One thing that maybe you're kind of looking at here, funnily, is that you actually see these negative return. Thank you. And this is partially being driven by this negative complementarity. So most people don't go into engineering or medicine, right? And so what we see is very small but negative returns to doing STEM versus academic. Okay, and this is mostly being driven by people who basically don't go to college. So in Sweden, I think we have like 30% of people go to college, but the other 60 to 70% don't. And it turns out that, I'll show you in the next slide that there's a negative interaction between doing STEM versus academic and and staying a high school graduate. Okay, and that's this next slide. So I just want you to focus on the middle line here. Okay, so this is holding everything else the same. Okay, so looking at the earnings equation, what happens if you just change the high school track they went to, right? So take someone who, went to medicine or engineering, okay? And then ask what happens if I take their, I take their STEM and their track and switch it from STEM to academic or from academic to STEM. And you can see that we see some positive returns to that, right? They get higher earnings if we change their high school track from STEM to academic. What you see here, and this is what's driving those negative results we saw earlier, is that in terms of high school, they're earning lower wages compared to the academic track, okay? So I think I'm really running out of time. We have a lot of other stuff that we do in the paper. And as I said, we're doing a major revision. The major revision that we're doing is that we have now application data. So we can see them rank 12 programs. We have it clean now. We're estimating a model, an exploded nested logit, multinomial logit model, where we can estimate the preferences that individuals have. And from that, we're going to be able to get even more information about the type of students and their preferences for doing these different majors. Okay. I think I should probably stop there, right?
Yeah, because there are actually two more questions.
Okay, great.
Just came up.
Yeah.
You could ask Joanna if you want to ask this question directly online.
Joe, do you want to ask your question?
Hi, Greg. Thanks. This is really interesting stuff. I was wondering, it looked like some of the stuff you showed us in terms of the complementarity between ability and college attendance seems reminiscent of, say, Carnera, Heckman, Vidlichil. That's the paper that I would think of to sort of establish my prior about those complementarities. I guess the big difference is you have multiple factors here and it's a different setting, but can I think of these results as being in the same vein?
So in my previous work with Jim, and then also in his previous work, they show complementarities between ability and schooling achievement. So do you get a high school degree, or do you go to college and get a college degree? And what we're doing, the difference here is we're looking at differences in specialization, right? So taking someone from two people who graduate from high school, one doing an academic versus doing a STEM track.
Right. Okay.
It definitely connects to that, and we're here building off of the work that we started with Jim, but yeah, it's cool. That's the main difference. Yeah,
that makes sense. Yeah, thanks.
And for you also here, right? Do you want to ask directly?
Well, I guess it was more just to John's point about grades, is that there's in the Swedish context, you often don't have grades per se; it's more pass-fail. But one thing that can be used, I guess, is the credit completion rate, because then because you can't really fail Swedish classes per se, you continue to retain. Actually, a very good measure of ability in college is how quickly they pass, or the pass rate condition on the registration.
Okay, that's super interesting. So yeah, we have that data. So we have credits. Oh, sorry. So the point was that it's hard to get good grade data in Sweden. But one thing you can look at, which is something that we haven't, which is very interesting, is that we do have credit data. We can see when they complete the credits. And in Sweden, you can keep on taking tests to eventually finish. And that could be itself a measure, like a grade measure, independent of not the actual grade, but yeah. So thank you. That's a very, very good idea. Yeah.
Are there any other questions? Also online.
Online.
Yeah.
Yeah. Okay. Well, thank you very much.
Are there any other questions of the people online?
Oh, thanks very much for inviting me to present here and organizing the conference. It's super nice to be here in person after a year and a half of being isolated. So structural models very often involve assumptions about the distribution of unobserved states. We know that our models are never exactly right. So we should check whether the counterfactuals and policy evaluations that we do with these models are not highly sensitive to the distributional assumptions. In this talk, I will propose a framework for doing these sensitivity checks with respect to the distributional assumptions in structural models. And this is work in progress with Tamara Broderick, Ryan Giordano, and young Christian Hutter. I'm very fortunate to have some amazing collaborators. Cool. So why do we use structural models? We use structural models to leverage on economic theory to make decisions or to make recommendations for policymakers to make their decisions. For example, there's this really cool paper by John Rust on optimal replacement of bus engines that describes the process of operating a bus fleet over a major city in the US. Unfortunately, we have to make some assumptions to make that model work. So particularly to make to come up with analytic solutions to these models, we often are required to make very special assumptions about the distributions in the model. So in the Rust model, we have to assume the Gumbel distribution to have analytic solution to the value function and the conditional choice probabilities. So our solution of the model depends on the distributional assumption. Therefore, the counterfactuals and policy evaluations that we back out of the model also depend on this assumption. So hence, we should do a sensitivity check to make sure that our conclusions that we make with the structural models are not entirely based on this very special convenience assumption of the Gumbel distribution, for example, in the Rust model. So what can we do? How can we do this? Well, we could try things other than the Gumbel in the Rust model. For example, we can resolve the model with a few different choices of this distributional assumption. Problem, this is probably computationally expensive because you will lose the analytic solution. Aside from that, you can only try a handful of different distributions, but particularly those that you can write down with an analytic form. And most likely you will not be trying the ones that matter. We can try something else. We can try estimating the entire identified set of structural parameters. And this will give us the entire identified set of the counterfactuals. This is probably really hard. This is probably super computationally expensive. And this is probably a lot more work than necessary. For example, if I'm interested in a one-dimensional counterfactual and I have 10 structural parameters in my model, I would be doing a lot more work than necessary. There's some really exciting current work in this direction. Specifically, there's a paper by Tim Christensen and Ben Knoll that solve an important special case of the sensitivity problem in structural models that have constraints that depend linearly on the assumed distributional assumption. And they leverage the structure of phi divergence neighborhoods with their convexity properties to provide a very elegant solution to this problem. What I will do is propose a new framework to characterize sensitivity to structural models to distributional assumptions, where the dependence on this assumption is completely general, as long as it's smooth. The sensitivity perturbations in this assumption, in the distributional assumption, will be over neighborhoods described with a general metric. This framework promises to be computationally tractable, and this is the very much ongoing part of the project, even automatable. So those derivations that are required perhaps can be actually automated with automatic differentiation. So let's fix an example and remember some notation. We'll use John's paper on optimal replacement of bus engines. And let's say that the counterfactual that we'll be interested in is to make this decision, a forecast, whether Harold Zerker will be choosing to replace his existing fleet of GMC diesel engine buses with really cool new electric vehicles or not. So the main observation on the slide, I'm going to put up a lot of notation. We're going to recall sort of at a high level the entire Rust model. I will not really need that notation later on. The main observation here is that everything that comes out of the model depends on the distributional assumption F that happens to be Gumbel in the Rust model. So feel free to not try to memorize the notation here. So every month, Harald Zerker has to make a decision of whether to replace an engine on the bus or do regular maintenance. So we know this by D. There's two choices, 0 and 1. These decisions incur a flow cost, pi, that depends on which decision you take. So there's two structural parameters that come into this flow cost function, theta 0 and theta 1 give you the monthly cost of either maintenance or replacement, and the cost of maintenance depends on the observed state in the model, which is here the mileage of the bus X. So this is a decision every month, and the way Harald Zerker solves this problem is to look into the entire future, calculate the expected net present value of costs of taking a certain one decision or another decision, and doing the best action. So we have this object V, which I will call surplus or cost or net present value of cost. That is the optimal cost that you will incur by operating these buses in an optimal way. So in particular, in this Bellman equation, we see that the distributional assumption of Gumbel over the shocks to the monthly service costs enters. Hence, the value function, the surplus, depends on the distributional assumption F. And the choice probabilities implied by the model for the two decisions given the state also depend on this assumption F. Right, so once we've solved the model and have the conditional choice probabilities, we can write down a likelihood and we can optimize it and get an estimate of the structural parameter. And we see that that quantity that we're estimating, the theta, the structural parameter, once we put the data into the likelihood, it also becomes a functional of the distributional assumption that we put on the shocks, right? And finally, we can plug in our estimate of theta into the surplus and get an estimate of the surplus that fits the data the best it can. Now, once we have estimated the model, we can do what we want to do. We can do counterfactuals. So suppose that the electric bus compared to the old school bus has a cheaper cost of monthly maintenance. So here I have the cost of monthly maintenance, but it has a double of the cost of replacing the battery compared to replacing the engine on an old school bus. All right, so the question is, what would be more optimal for Harald Zerker, the yellow bus or the blue bus? And the way we will forecast this is we will compute the change in surplus to making the switch, right? I will call this K. This is the scalar counterfactual quantity in the Rust model. And if this is positive, then we will forecast that we should do the switch. If it's negative, we will forecast that, well, we shouldn't replace the technology. We should stick with the cheaper old technology. But the main point, this quantity depends on the assumption of Gumbel, if you put Gumbel in, or whatever other distribution that you picked in solving this model. So to make our conclusions based on the counterfactual out of the model more reliable, we should do sensitivity analysis with respect to this F. And that's what I'm going to talk about. All right, our framework. So this is the notation that matters. I will denote by F naught the assumed distribution of unobserved variables. For example, it's the Gumbel distribution in the Rust model that gives you analytic solution for the surplus and the choice probabilities. We will denote by theta the structure, the vector of structural parameters, and I'm explicitly stating that these things depend on the assumption that you put on the unobservables through the estimation procedure that you use to estimate theta. For example, in the Rust model, theta is the monthly cost of maintenance or the cost of replacing the engine. I will denote by K the scalar counterfactual quantity that you want to back out of the model. And typically it will have the structure. It will depend on F in two different ways. It will directly depend on F through, for example, the expectation operator on the Bellman equation. And it will also depend on F through theta, through the structural parameter. And here's what I propose we do. So we start out with our distributional assumption F naught. We say we want to change this assumption, we want to perturb it. So we will need to fix a metric on a space of probability distributions that will tell us how far we have perturbed this assumption. Once we have a metric row, we can fix a delta room around F naught, and we can solve this problem. We can see, well, how much can the counterfactual change if I perturb F naught in this delta ball around the assumption that I'm making? So if I do this for every delta, I will construct what I call the least favorable path of distributional assumptions. So what we propose is a greedy algorithm to solve for this path. The greedy algorithm solves the local version of this problem number one, and it iterates the local version to actually produce the entire path. So the high-level overview is as follows. First, we solve problem number one locally. Two, we update the distributional assumption. Three, we update the entire solution of the model with this new distributional assumption F delta. And then we repeat. And we do this as long as we need to kind of like verify that the sensitivity of the counterfactual is hopefully not too large. So what do I need to tell you to be able to use this, or to understand, or to convince you that this is usable? Well, I'll probably have to tell you how to write down and how to solve the local problem. Then I will need to tell you how to integrate the local solutions and actually produce this path with favorable distributions. We'll need to talk about how to update F delta. So from a local solution, how do we extrapolate it? And finally, I'm claiming that I can resolve the model, I can get the updates to the solution of the model along this least favorable path without requiring you to resolve your model. So we'll probably need to have a slide on that. Cool, so what is the local problem? This is just a restatement of the problem we're trying to solve. We're trying to soup the counterfactual over a delta ball of our distributional assumption F naught. To obtain a local problem, we replace K, the counterfactual, with its derivative. And its derivative with respect to the distribution assumption F. And then we replace the distribution itself, we replace the least favorable distribution F delta in the main problem with the direction of most rapid change in the counterfactual K. Why are we doing this? Hopefully that will become clear by the end of the slide. Challenge. Distribution, the space of probability distributions is not linear. So what is a local problem? How do I do derivatives with respect to a distribution if it's a not linear space? You cannot do the usual differences that you've learned in high school. Solution to this is scores and influence functions. And we actually worked with this because you've all done maximum likelihood. So the way we can differentiate is pathwise. What I have to do is fix a one-dimensional parametric model, F sub H. Okay, and this model has to be smooth in the sense that it has a score function. And the score function, you actually know what it is. It's the derivative of log density along that path. Okay, so the score is really the direction of this one-dimensional path. Why are we doing this? Well, we're doing this because once you fix the path, you can compose F sub H with the counterfactual, and now you have a function of a one-dimensional variable H, which you know how to differentiate. So we now are able to differentiate K with respect to F. So there's some kind of a notion of a derivative operator, which I denote by dk, and it operates on the space of scores, which happens to be L2 of the distribution at which you're differentiating K. All right. This derivative operator has a Rees representation because it's a derivative operator on L2, Hilbert space. This Rees representation has a Rees representer, and that's what we call the influence function. So I sub k is the influence function of the functional k And it's a device for us to compute these derivatives. And most importantly, this object I sub k solves the local problem. The local problem is I want to find the direction of change in F such that it's bounded, it has a bounded size, and it maximizes the infinitesimal change in K. And that problem is solved by the influence function. Yes?
So just to be concrete, let's go back to the bus replacement problem. So the way we want to think about this is at each value of, say, total miles on the bus engine, we're going to figure out the density of replacement. And basically, we only need to see the density over we see the number of replacements, and that gives us the density of F at a given value of the state variable. Is that cool?
Yeah, in the Ross model, F. Yeah, so the question is, let me try to give you the answer, and hopefully that will also summarize the question. In the Ross model, the distributional assumption F is about the shocks to the monthly replacement and servicing costs. We never observe it. We cannot estimate it. We don't have data on it. It's the latent state of the problem. The only thing we can do is assume what it is. Right. So we solve the model under the assumption that we know what the distribution is, and most of the time that's Gumbel. Now, if I change Gumbel to something else like a normal, you have a different solution. And you have a different value of this counterfactual K, the change in surplus from switching to the EV buses. What we're doing here with this local problem is saying, well, let's say it's Gumbel, but I'm going to perturb it slightly. I'm going to change its shape infinitesimally of the entire, think of the CDF function to the Gumbel, and say I'm going to distort it by a very, very little bit throughout the entire profile of the Gumbel CDF. That perturbation is described by either a score, if you know in which direction you want to perturb it, or what I'm doing here is I'm finding the direction where the counterfactual changes the most from this perturbation. And that is what I'm calling the influence function. So it's the optimal infinitesimal direction of perturbation to the Gumbel assumption for the purposes of this change in surplus in the Rust model. Does that help? Thank you. Excellent.
Intuitively, it's like the gradient. If you find an additional calculus, the gradient is the direction of rest.
So John has a really nice point. Let's make it simple. Let's say we don't have Gumbel, we have a multinomial distribution on the shocks. You're just differentiating the weights of that multinomial distribution. Thank you, John. So we've simplified the sensitivity problem by passing on to this local problem, which is tractable. After all, how hard is it to optimize a linear function? But we would like to go back, right? So I have a solution to this simpler local problem, and then I have to go back and try to get a solution for the original problem of actually finding the least favorable distribution of shocks in a delta neighborhood around Gumbel. So how do we do this? Well, we want to combine local solutions and back out the least favorable path. And literally what we'll do is integrate the local solutions. We'll solve an ordinary differential equation that says, I want the least favorable path, and the least favorable path is described by this equation that says the direction of the path is the direction of most rapid change in the counterfactual K at every point. And you have to start the path at the distribution that you assumed. So let's say Gumbel in the Rust model. I challenge. The space of distribution is not linear, so it's not quite clear how to actually write this down and solve it. Solution, well, we just need to do it the right way, and here we can use geometry. So we're really looking at a space that's not linear, it's curved. So if we formalize that with the manifold parameterization, we'll be fine. So we handle this linearity with exponential ordered spaces, and There's this reference that is crucial for this, Pistorius and P 95, that provide this sort of mathematical machinery that we're leveraging. Finally, in a lot of these structural estimation problems, you have some constraints on the distribution of unobservables. For example, you want it to be mean 0, and you want it to have variance 1, or you want to have some other shape restrictions. We can accommodate this in this framework by imposing corresponding constraints on the right-hand side of this equation. So I can take the influence function, this direction of most rapid change, and I can project out coordinates. I can make sure that it satisfies these restrictions, and then the entire solution will also satisfy them. Okay. So we've solved the local problem, and we now theoretically know how to combine local solutions to get an answer to the actual problem of sensitivity analysis. But in terms of practicalities, how do we do one step of greedy? Right. So one step of greedy algorithm will be a linear approximation to the solution of this equation. So the naive thing to do would be to do it linearly. I will literally take the log and look at the derivative of the log and do a difference instead of a derivative, and that will lead me to this formula. So if I have a solution at time h, or h away from 0, and I want to extend it by epsilon, I just use this formula. I take the influence function, the direction of change, and I scale it by epsilon, and I put it into this formula. Problem is this: influence functions are often unbounded, and they also mean 0. So they're definitely taking on some negative values. And if those negative values are unbounded, then I'm going to get some negative values for my density, which shouldn't happen. Again, the issue here is that the space of distributions is non-linear. We just have to deal with that somehow. And the solution to this practical challenge comes out of the parametrization that we do. So it suggests a formula that's slightly different from the one here, but it coincides with the linear formula up to first order. If you do a Taylor expansion of exponential function, you will see that this is up to first order, exactly the same formula, but you have to plug in a finite epsilon, and this works for any epsilon. All right. So I made this claim that while doing this greedy algorithm, I can update the solution of the model along the least favorable path without resolving the model with the new distributional assumption. So let's kind of sketch how that works. So let's assume the structural parameter is a scalar. Otherwise, let's just consider each coordinate separately. And what we can do is use a linear approximation to the change in the solution of the model. To do the greedy algorithm, we have to work out these influence functions, practically for every element of the solution of your model. So we can just leverage them to compute the derivatives and do linear approximations to the change in value of the solution. So if I want to update the value of my structural parameter when I make an epsilon step away from my current distribution assumption f sub h, well, I take my current value of the structural parameter and I add the value of the derivative in the direction that I'm stepping away from fh, right? And the way to compute this derivative is through inner products and the influence function of the parameter theta against the influence function of the direction of change in f, which is going to be the influence function for the counterfactual quantity k. Cool. All right, so this is one step, and if you want to compute a change for the over the entire path, least favorable path, you just use fundamental theorem of calculus that says, well, you have to integrate the derivatives, and that will give you the actual change. And of course, we can on a computer just discretize it and do it kind of like piecewise. All right. So I probably don't have time to do this exercise of deriving the influence function for the simplest possible functional, but it is meant to convince you that it's doable, even though it's a little bit tedious. And the good news is that there's promise that this can be automated. So really what I require to do this algorithm is that you work out analytically with pen and pencil these derivatives, these influence functions for the solution of your model. by the way, you should be doing some of that work when you do inference. If you do standard errors for your maximum likelihood estimator, you'd be taking some of the derivatives to begin with. But anyway, so the good news is that this can be automated with automatic differentiation. So that would be really, really nice. Yeah, and let's come back to the Rust example and see what we get. So here we're doing sensitivity analysis to the Gumbel assumption for a counterfactual change in the long run net present value of cost of servicing the GMC bus as compared to this new technology, the electric bus. So what we do is we compute the upper bound by solving the max problem and the lower bound by solving the corresponding mean problem in the change of this surplus over a delta ball of probability distributions around Gumbel. Right, and here I'm plotting the upper bound and the lower bound. And with the way I set up the counterfactual, it seems like Harald Zerker should be switching to electric vehicles because the change in surplus is positive. And our sensitivity analysis has verified that this is not because of the convenience assumption of Gumbel. This is actually a robust feature of the model. Right. Corresponding to those upper and lower bounds, you get the least favorable distributions as well. Right, so this is how the Gumbel assumption has to change. So in green here we have Gumbel, and for the upper bound and lower bound at delta equal to 0.5, the alternative assumptions to Gumbel have to look like this CDFs in yellow and blue. All right, so I proposed the framework for sensitivity analysis to counterfactuals in structural models with respect to distribution assumptions of latent states. Our framework accommodates structural models with general smooth dependence on F. So for example, yesterday we saw a presentation where the agents in the model were doing something similar by taking a ball in KL over the normal. So it, to me, sounds like would give you a pretty interesting dependence on the normal distribution assumption for the econometrician. And I have hopes that this will apply. Our framework allows for perturbations over neighborhoods away from Gumbel in a general metric. For example, we can use Wasserstein metric. And there's a technical important point here with Wasserstein. Wasserstein allows these perturbations to change the support of the distribution. So if you assume the distribution that has support in 0, 1, and it happens that the more the sensitivity is with distributions that have support in -1 to 1, when you do this with Wasserstein, you will uncover that. Whereas if you do it with divergence, you will stay on 0, 1. Next point. So our framework does not require resolving the model under any distributional assumption other than the one you started with. And we hope to automate kind of the crucial element of applying the framework, the derivation of the inference function. Main limitation of this. So the nice greedy algorithm doesn't come for free. The main limitation is that it doesn't have any guarantees to back out the entire identified set of counterfactuals for you. It can only do local analysis. So it will converge to some local maximum and local minimum, and you will never know whether that's the global maximum of the counterfactual or not. So we feel that it's perfectly fine for sensitivity analysis, and we'll probably worry you more when you're estimating your model using the same kind of greedy algorithms. Finally, questions, comments, feedback are super welcome, highly appreciated. If you want to try this in your model, please talk to me. I'll be super excited. And yeah, this presentation is based on my thesis work. There's a couple of papers there, and it's joint work in progress with my amazing collaborators, Tamara Broderick, Ryan Giordano, and Jan Christian Hutter. Thank you very much.
Fantastic. So I think there was one question coming right in from Michael Keen. So Michael, if you want to start.
Okay, I was just wondering if you had a static discrete choice model, I think it's true that in a static discrete choice model, if you think about changing the error distribution, there's always some equivalent change in the payoff function, like the deterministic part of the payoff function, that would lead to the exact same choice probabilities. Right, so if you took a logit model and you depart from the Gumbel assumption, you could find some equivalent chain, generalization of your X beta.
Choice probability is
That would,
exactly the same. I think the choice probability, so I think of this in terms of logit and probit regressions. You can work out how the coefficients will change. You can write down explicit formulas for that, at least in principle.
Yeah.
And you can probably write down implicit formulas for how the probabilities will change, but I don't think they will stay exactly the same. I think they will also change.
okay, I guess I would suggest you look into that, because I think you really can, in the static case, come up with a generalization of the f of x beta.
Yeah, the first exercise that I applied to was the logit regression. And what I was able to do is by tweaking what they call the link function in statistical literature, you can do things like changing the sign on the coefficient, for example, over a regressor with certain changes to the logit distribution.
But I just was wondering whether that same idea would carry over to a dynamic model. I don't really know. And whether you could have somehow equivalently done this by looking at going non-parametric on the deterministic part of the payoffs.
Yes, if you look at the static model and you make the linear component, let's say you put in some dictionary of transformations of your variables, yes, you would be converging to the choice of the link in that exercise will matter less and less as you increase the flexibility of the analytic part of the regression function. Yeah. So I'm
just curious. Yeah, I'm just curious why why is it better or more interesting to look at deviations on f rather than on the current payoff function, the deterministic part? Might that be easier, or what are the advantages?
You're doing that implicitly. You're changing f and you're tracing through how the deterministic part of the payoff function will change, and then you're propagating that to the counterfactual. That's But here, there's just like a ton of chain rules in this derivative calculations, and it's all done by calculus. Yes, it's happening.
Yeah. I know I've heard, if John is there, right? I've heard John argue in the past that if you go flexible enough on the current payoffs, you don't have to worry about assuming Gumbel.
Yes, if you can.
I'm wondering if he agrees with that.
In the dynamic model, I have less of an intuition for what non-metric means. Yeah.
Value function differences that explain that choice problem, right? I'm afraid I couldn't hear you.
No,
but I think we're also shortly. I mean, we're also running out of time, so I think we have to.
I'll answer them offline.
Right.
Perfect.
Thanks, John.
So the conclusion that I made a mistake in using the value decision, should I use? Is that robust or not robust?
In my counterfactual, it didn't matter. So you're good. You're good. It was a good assumption.
Okay. I'm sorry to kind of cut it short here, but we're really running out of time. But I really encourage you to kind of get in touch with Yaroslav and kind of discuss things, and also, of course, with Gregory. So thanks so much for this very interesting presentations. Thanks also a lot to Mike Keane and the others who were there and asking the questions. So I also encourage you, if you want to, you can keep discussing. But I want the other people to let go for lunch, because we will restart in now less than an hour. So like local time, 1:30 p.m. Not sure what this is in Australian time, to be honest. Sorry for that. So thanks so much for participating. Yeah, see you soon.